For the computer architecture course, BISA, Bob's Instruction Set Architecture. BISA is a 16-bit word addressable only system. It includes 16 different 16-bit general purpose registers. It's built specifically to run on the Altera DE270 machine. And an interesting part of it is it doesn't have any branch instructions, but it uses jump and jump register like instructions to allow you to branch around. And it's extremely MIPS-like. General purpose registers, if you know MIPS, you know these are going to be very similar. We have a always zero register. We're going to have a return address. We're going to have function, parameter addresses, temporary registers, non-temporary registers, stack pointer. And my face is in the way of the memory pointer, which is not MIPS-like, and the return address. The instructions supported, most of these are pretty familiar if you're familiar with MIPS. However, the jump register on zero and jump register unless zero might not be familiar. Basically, these are jump registers when we test if something is zero or not. So we use our set less than and set equal operators to determine if something should jump, and then use JROS or JRUs to jump in those scenarios. We use something built into the machine called sysclick1, which allows us to use a clock divide controlled by switches on the board. We use the falling edge to clock registers and the rising edge to change the next state in the sequencer. And the big caveat here is the low clock time must be long enough for the longest propagation path. So an interesting part of BISA is the use of a memory pointer, which is really convention, but it's a convention use of the MP general purpose register, which I think is really interesting. If you're familiar with how machines operate for the most part, you know that the stack grows down and the heap grows up. But with this instruction set, we actually use memory pointer as a pseudo-like heap location. Although there's no heap, it's just basically stack memory and non-stack memory here. So whenever you're adding a new value to non-stack, by convention, what you do is you increase the memory pointer so you know where the next available location of memory to safely put data is. And here is the BISA block diagram. Some interesting points of note is the barrel shifter over here, multiplication hardware over here, and the comparator over here. Just an important caveat here is that these pieces of hardware are not built at the lowest bit level currently as of recording on Monday evening. However, they're built in high-ish level VHDL programming. All right, the assembler, what this does is it generates a MIF file, which we put into the machine to read our instructions. The way my assembler works is each instruction, the original one that the system programmer put in, is in a comment next to the machine created instruction. We support numbers as decimal or hexadecimal. We support the LI pseudo instruction. We support labels. Comments are once a hyphen is seen in the instruction, the system programmer instructions. We support ASCII Z, and we support the EQU directory. And that went through, and that created the assembled version. Now I'm going to bring this up, program.mif file. And at the very top, you can see that there's some values that Cordis and our VHDL code expects with a loaded MIF file. And then after that, you can see the code that's been generated based on our input. Here you can see comments denoted by hyphen. Here, those comments show the values that the system programmer's instructions were used to create these machine instructions. And on the second, third, and fourth line, you will see our li pseudo instruction that was loading the value stored by label memory start into the FP register. And LI, what that does is first it clears the register with an AND I on 0, and then it loads the bottom two values with an OR I statement, and the top two values with a load upper immediate statement.
Okay, so we use the emulator to show how we expect each program to run when we move it on to the lower level system. We support a debug mode, which will show each instruction being executed, as well as each register value at each instruction, and a delay mode where we actually delay each instruction by 1 second. Go to the emulator in the normal mode with no debug on and no delay on. We put in 6 and 24 as inputs, and we see 144 as the output. The emulator on delay mode, the instructions start, load in the memory, and you can see a quick delay of about a second for each instruction to be seen. This really allows me to create small instructions, small programs, and look at each instruction easily as they're actually occurring. And now we're going to demo this on the hardware. This is Cordis. This is a program we use to load our program into our DE270 board. I am loading the MIF file and writing the data to memory. Now, if you take a look, our board is in a clean state, and now we can undo our hold and take a look at data in the application. Here you see the debug switches. Debug information goes in this right hex bank here, and based on the switches that are set, you can read different values here. So right now, with this being set here, this is number 2, which is the location in memory that's being read. If we change this to 1, now we're looking at the values of the different registers, and that's controlled here. These 4 switches on the right side are the registers that would be read. When all of them are on, that's looking at register 15. When all of them are off, it's looking at register 0, and everything in between here. When we change this to 3, it's looking at the next instruction that's going to be executed. When it's on 4, it's looking at the current instruction. And when it's on 5 and 6, it's looking at the values that are in register 1 and register 2 specifically. I'm sorry, not register 1 and register 2. ALU outputs 1 and 2. Over here, switches 10 through 8 control our clock speed. So right now, since it's on 0, it's running very slow, but it can start to go faster as we change the speed here. All the way on the left-hand side here is the different process stages in our sequencer. So as this goes faster, as we make the clock go faster by lowering the clock divide, you'll see that start to go extremely fast. And where we can make it go very fast here, now that we're at a solid speed, let's take a look back at the serial emulator. And this is our multiplication problem. Let's see, select the number. I'm gonna type in 24. Then it's going to ask me to type in another number, and I'm going to type in 6. And now it's going to multiply these two values together and spit out a response for us. And that response is 144. And then it goes back to the beginning. Some interesting logic I noticed along the way. An easy way to multiply by 10 with low-level programs. Basically, you shift the original value by once, and then you shift the original value 3 times, and you add the results. And that gives you the value multiplied by 10. Shifting it once multiplies it by 2, shifting it 3 times multiplies it by 8, and that multiplies, if you add those together, that is the value multiplied by 10. This helped me in one of my areas of my program, and I thought it was pretty interesting, and I wanted to point it out. And that's BISA. Thank you. Any questions?